Okay, so we're going to do p-series in this video. So a p-series is a specific series. It's only of the form 1 over n to the p. So if you have 1 over n squared, that's a p-series. 1 over n cubed, that's a p-series. 1 over square root n, that's also a p-series. Those are all p-series. 1 over 2n cubed, that's a p-series because you can pull the 1/2 out of the series and then do 1 over n cubed. So this is a p-series also. What is not a p-series is if you have 1 over 2n cubed plus 7, okay? So this is not a p-series. Things you can't do with p-series is add a number, add another term. Anything that you can do with p-series is only multiplying by a constant. That's the only thing that you can do and still say that you're using the p-series test. All right, there's a special case of p-series, which is called the harmonic series. That's where your p-value equals 1. For that special case and that special case only, you can say harmonic series test, and that is the sum 1 over an plus b. So any version of that you can say is the harmonic series, and say whether it will converge or diverge based on the harmonic series, not a p-series. So 1 over an plus b is called the harmonic series. For example, 1 over 2n plus 3 is called the harmonic series, okay? You could also call this a p-series if the 3 wasn't there, but if the 3 is there, make sure you say harmonic series. All right, let's see if we can use integral test to find out what values of p would cause this series to converge or diverge. So we're going to start with p equals 1. So p equals 1, that's the harmonic series, but I would be trying to find out if 1 over n to the infinity of 1 over n converges or diverges, because p equals 1. So we do the integral from 1 to infinity of 1 over x dx. This ends up being natural log of x evaluated from 1 to infinity. I'm skipping some mathematical notation here, but hopefully you can follow along. This is natural log of infinity minus natural log of 1, which equals infinity. So this sequence, this integral diverges. So this series will diverge. Okay, let's check out what happens when p equals 2. So we're figuring out whether the series of 1 over n squared converges or diverges. Let's go 1 to infinity, 1 over x squared dx. That antiderivative would be negative 1 over x. So it's negative 1 over infinity minus negative 1 over 1. And that goes to 1. So this one will converge. Okay. And you can kind of see that this is going to converge because when you add 1 and you do the antiderivative of x squared, your x is going to stay in the denominator. All right? So that's important to know when we start making rules for our p-series tests. So p equals 1/2. Let's see what happens. So integral from 1 to infinity of 1 over x to the 1/2 dx. Well, that integral is going to be 2 root x evaluated from 1 to infinity. Now notice when we integrated x to the 1/2, it ended up that my x went into the numerator, and when my x went into the numerator, now I'm taking infinity of something that's in the numerator, so this is going to go to infinity. Therefore, this p-series is going to diverge. So hopefully what you can deduce is that if p is less than 1, it's going to diverge because your x value is going to end up coming into the numerator. And if p is greater than 1, it's going to converge because your x value is going to stay in the denominator. So p-series test, if we make a general statement of it, is if p equals 1, it's going to diverge. And this is also called the harmonic series. If p is greater than 1, it's going to converge. And if p is less than 1, it's going to diverge. These two are by p-series. This one you can say by harmonic series. All right, p-series test is probably everybody's favorite test because all you have to do is recognize that this is a p-series. And this n can be rewritten as n to the 3/2. And 3/2 is going to be the p-value. The p-value is greater than 1. Therefore, series converges by the p-series test. And that's all you have to do for p-series tests. Okay? All right, we're going to do the comparison tests in this video too, just so that I can get them done. The direct comparison test is the first comparison test that we're going to learn. This one says that if you have two sequences that are greater than 0, if one sequence converges and you can prove that another sequence is smaller, so this is smaller, then something that you already know converges. If you can prove that a sequence is smaller than a series that you already know converges, then you can say that series is also going to converge. Similarly, if you can prove that a sequence diverges and you can prove that another sequence is bigger than a sequence that you already know diverges, then you can say the bigger sequence is going to also diverge. Sorry, I should have said series. The other series is going to diverge. Okay, let's do some examples of this. So what we want to do is we want to compare this to a series that I kind of already know. Two good series to use when you're doing comparison tests are p-series and geometric series. I'm going to compare this to 1 over n cubed. Now, 1 over n cubed converges by p-series, right? Because p is 3, which is greater than 1. So if I know that this series converges by p-series, and I can make the statement that 1 over n cubed plus 1 is always smaller than 1 over n cubed, and I can make that statement because this is adding 1 to the denominator, so it's making this fraction smaller than this fraction. If I can make that statement for every value of n bigger than the starting value, then I can say that this series converges by direct comparison. Okay. try the next one. So this one I'm going to compare to 1 over 3 to the n, which is the same thing as 1/3 to the nth power. Now 1/3 to the nth power, you should know, converges by geometric series, right? Because your r value is 1/3 is less than 1 for a geometric series. If this converges by geometric series, I want to prove that this is smaller than what I compared it to. And I can say that. I can say that this sequence that I am trying to prove is smaller than the sequence that I compared it to. Therefore, if I know that this sequence converges and this sequence is smaller, I can say that my sequence converges by direct comparison. Okay. All right, one last one. 1 over square root n will compare to that. 1 over square root n diverges by p series, right? Because p is 1/2, which is less than 1. And since this one diverges, what I want to prove is that 1 over root n minus 1 is bigger than 1 over root n, which I can say because it's minus 1, so it's increasing the size of the number. And so therefore, if I know that this series diverges, then anything bigger than that is going to diverge by direct comparison. Okay? Awesome. One last test for this video is limit comparison. Now, what if you compare it to something and it's not smaller all the time, so you can't do direct comparison? Well, another test you can do is limit comparison test. And what limit comparison test says is that if you have two sequences that are both greater than 0, and if you take the limit of one sequence divided by the other, if that limit exists, it equals a number. That number is both positive and finite. Finite just means it doesn't equal infinity. So it equals a number that is positive. Then whatever one series does, the other series does with it. Okay? So if the limit exists, then what one series does, the other series will do too. They will converge or diverge together. All right. So what I try to do when I'm doing limit comparison tests is try to make it so that a limit would exist if I divided one by the other. I look at the exponents, n to the 4th over n to the 5th. N to the 4th over n to the 5th simplifies to 1 over n. Ignore the leading coefficients, that doesn't really matter. What we're really looking at is the exponents of the function, of the sequence, sorry. So if I have the series 1 over n, I know that this one will diverge by harmonic, right? If I know that this one diverges by harmonic series, and I can take this sequence and divide it by this one. So if I do the limit as n goes to infinity of this sequence divided by this sequence. Let's just simplify by multiplying by the reciprocal of 1 over n. Okay, so I multiply by n over 1. Okay, this limit, now look, my exponents are the same because I divided by 1 over n. When I simplified this, it helps me get the exponents the same. Now the exponents are the same, and this limit goes to 1/4, which is a positive number, right? Finite just means that it's a number. So that's a positive number. If that's a positive number, then whatever this sequence does, this sequence will do. So therefore, it diverges by direct comparison. Okay. Feel free to pause these videos at any time and try the next problems before I actually do them. You could do that with this one if you want to. You could pause right now and then try it and then see whether or not you get the right answer. But if I simplify the exponents for this one, I would get 1 over n cubed, and I would know that this converges by p series, right? And if I know that this converges by p series, I could not do direct comparison with this because this converges by p series, but I can't prove that this is smaller than this one. This one is going to be bigger than this one, so I can't do direct comparison. I'm going to do limit comparison and divide that by that. Simplify by multiplying by the reciprocal. Sorry. So this equals 1 over 1, which is positive and finite. So it's a positive number. So if this equals a positive number, then whatever this one does, this one will do. This one converged, therefore this one is going to converge. And sorry, I just noticed I made a mistake. This should not say direct comparison. This should say limit comparison. Okay. All right, that's the end of comparison tests. Watch the next video if you missed any of the other series tests. See you guys.